journey basically started with Naylor's having a look at our own carbon footprint and saying, what can we do to reduce it? So we did what everyone else did. We measured our carbon footprint and we decided we've got about 400 Ford Ranger utes, which Jacinta doesn't like. And we can change those to hybrids, and we can have all these things like solar panels on our site sheds, etc. So we're doing that, but we really wanted to know what would make the biggest bang for our buck. So we got interested. We like building in timber. We got interested in engineered timber, and we commissioned a report from a company called ThinkStep to pretty much set this process up and tell us what the effect would be if we just changed one building, from concrete and steel to timber. So basically what we're measuring is, and a lot of you all know this obviously, but I'll run through it anyway, CO2 equivalent. So on the left-hand side there, you'll see the sort of thing you see in a bag of chips in the supermarket. Tells you how fat you're going to get, how quickly. And on the right-hand side is what we call an EPD, so Environmental Product Declaration. Ultimately, every piece of building material you buy or you go to install will have an EPD value. And effectively, those are the figures that we use to calculate the carbon content of that component of material. And those EPDs take into account, on our calculator, take into account where the product comes from. So you'll see as we go through the presentation, we've used, in some instances, European spruce, but we've measured the amount of carbon used to get it on a boat from Austria to New Zealand, etc. The whole carbon cycle, pretty obvious. We know trees absorb CO2. Trees are a bit like humans. When they're young, they don't sort of suck up much oxygen. As they get through puberty, they use a lot. And as they get towards the end of their life, like Grant and myself, they sort of slow down a bit, So ideally, what you want to be doing is using that timber and replanting to keep it going. So if we're going to cut down the Amazon forest to build timber buildings, it's not really going to work. But if we're going to plant another tree for the one that we cut down and utilize, it's a pretty good system. Some unabashed advertising for Naylor Love. This is a building we built, you can see 2017, so a few years ago. This was CLT in those days, manufactured by XLAM in Nelson, and the LVL structural components in the lower floor from Nelson Pine. This may or may not work on Teams. We'll just see how we go. So this is a student village at OTAGO Polytechnic. February 17th, we got components. March 24, which is 5 weeks later, we had a 5-story building standing. So the time to erect your timber components is really fast. You have to have them, and you have to have everything complete and ready to go for that to make that impact. The time to sling a LVL column versus a steel column is arguably similar. And the fact is people like working with lighter materials, so it's perhaps a little bit quicker. But the main difference is in the floor system. So in this particular building, CLT panels are going in as the floors. When that CLT panel is installed, you can work above and below it straight away. There was no propping, there was no other bracing elements. It was sort of 99% waterproof when it went in. So the speed of erection was really dictated by that floor system. On this particular building, the bulk of the CLT was untreated. So if it's coming from Europe, we call it naturally resistant because it sounds better. I have a personal like for sort of the larches and spruces and those sorts of materials. This was actually New Zealand pine, but it was still untreated because a lot of it was left exposed, and a lot of our clients don't particularly want that chemical treatment in all of their CLT or LVL. The reason it was consented quite easily is you can see the perimeter of the building is missing. So pretty much all those elements inside the building, apart from the wet areas. So the wet areas in that building would be CLT treated to 3.2. The rest of it was untreated. The exterior of the building was a totally separate system, almost independent of the CLT structure, but obviously held by the structure, but allowed you to have flexibility with what you built inside and outside the building. Some other timber buildings, Nelson Airport, probably the most complex timber building we have done. Here we go, this is one Holmes did, Cardboard Cathedral. Who would have thought it was actually made in timber? I'm sure all your engineers believed it was made out of cardboard tubes. This is a pretty good example. We'll pick up later on. Is a lot of the cost in these timber buildings is in the joints and detailing. So you can see the apex of that particular frame. Massive piece of steel, lots of fixings, all bespoke built. And one of the things we have to do, I suppose, as an industry is try to simplify these details. Not that you're going to build a lot of cathedrals. I think in that top right, you can see, so each cardboard tube in that cathedral has actually got a great big LVL beam inside it. As it turns out, it was one of the first hybrid structures that we'd built, although we didn't realize it at the time. So as we go through this presentation, we'll refer back to hybrid structures. So we basically have, if you think of the cardboard tubes as actually LVL, we have steel bracing elements taking seismic loads, and we have the effectively gravity loads taken by timber, which is a reoccurring theme as we go through the buildings we've built. This is another hybrid building we built in Queenstown. So it has a precast concrete, effectively a rocking shear core, and the rest of the building is built in timber. Now, this isn't a CLT building, it's stick framing. So the stick framing is supporting the concrete floor, a composite floor. So each one of those, actually it's not each one, I think every second frame has a timber joist, plywood deck, and then a concrete topping poured on top of it. So you wouldn't want to go around removing partitions later, but quite an interesting way to approach that build. Again, from the outside, this one chose not to express the timber. You wouldn't particularly know if it was a timber or a concrete build. Going quickly, I think it's a Rangiora High School by the looks of it, and some industrial buildings as well. The industrial build wasn't to save the planet, it was because steel rusts, and both Ravensdown and Balance continue to build fertilizer sheds and steel with steel purlins and steel cladding, and they all rust. This one has obviously LVL portals, I think glulam purlins, and plastic cladding. Stuff coming up, just because it's sort of interesting in terms of the local area. Ag research out at Lincoln, 2 buildings, one at the back's concrete laboratory, one at the front is an admin building built in timber. Sort of demonstrates that timber is not great for everything. So the lab has to have minimal vibration and minimal deflection. It's going to be built in concrete. The office building a bit more flexible. Ashburton Library, just started that down south. That's predominantly CLT. In fact, it's all timber. There is no concrete or steel seismic resisting elements in that. OTAGO POLYTECHNIC, again, all timber. It started, it's a trade centre, and AUTA1 in Auckland is due to start later this year as well. So there's a bit more interest in these big timber buildings. Most of them are actually coming from sort of government or pseudo-government departments. What carbon savings can we achieve? So what we did is we designed a classic 6-level concrete and steel building in Christchurch. And it was originally designed as a steel frame with steel K-braces and a chorus type floor or a concrete composite floor. Okay, in this building, we assumed a level site. We kept the foundations at the same, knowing that the timber structure will be slightly lighter. But for the sake of the exercise, we kept it the same. And we used the best possible EPD data everywhere. So what we did is we kept the steel K-braces. You can see those in red. And the red straps going across the CLT floor is effectively drag bars to take the loads back into those K-braces. So it would be nice to do it in timber, and you clever people can do it all in timber. I suppose it was just a fact that we thought from an economic point of view, it is going to be better to have $1 each way. Just explaining in terms of the elements that are concrete and steel. We then decided to measure all these things. So we got to it and we developed a carbon calculator type system with ThinkStep, which is basically a series of spreadsheets. And summarizing it down, what we're basically doing is taking your structural elements, measuring them in the appropriate form, whether it's cubic meters of concrete or kilograms of steel, depending on how the EPD data is presented. So at this point, we had on the right-hand side our concrete and steel building, and then on the left, what we thought was a timber building. But you can see it's still got shitloads of concrete and steel. So we're a bit despondent, and we thought, well, the carbon saving is going to be minimal, probably wasted our time. In event, the carbon saving was 90% on the structure. So quite staggering, the difference, given the amount of concrete and steel still in the equation. Now, how that basically works, as you all know, is we have this credit created by the timber structure below the line, and then we have the concrete and steel taking us back above the line. And effectively where those 2 points in the line stop is where we ended up. So you can see from that building, it would be very easy to make the structure carbon neutral. You wouldn't have to do much to the design. In fact, if we realistically lightened the concrete foundation to what it should be, I'm pretty sure we'd get that building back to zero. So that sounds great, but to me, being a builder, it doesn't mean a hell of a lot. So we had to convert it into something I can understand. So we saved 3,861 tonnes of CO2 equivalent, and that is the same as 2.5 million kilos of coal being burnt. So it's quite a staggering amount. Like, there is not a lot else you could do on this planet to save that sort of CO2 equivalent numbers. And it's great to drive your electric car and all those sorts of things, but it's a phenomenal amount. As an example, Naylor Love Construction is a $650 million per year company. That's how much building we do every year. We have 8 branches, and our carbon footprint, actually you might have a slide. Effectively, it's equivalent to 4 times our carbon footprint from the entire year as that one building. So by 2030, when we've done all these things on the left, changed our fleet, reduce this, reduce the other things, 2030, that one building will be the same as Naylor Love's carbon footprint for 4 years, and that's only one building. So it's a major difference in terms of what you can do by just selecting the appropriate materials. And remember, it was a hybrid building, it wasn't all timber. In terms of cost, is there any QSs in the room? I'll speak slowly, it's okay. In terms of cost, at this stage, we used European spruce for the exercise because, quite frankly, at that point in time, the New Zealand product was just too expensive. It's getting closer now with COVID and shipping and other industry pressures. But anyway, so this exercise, we used European spruce, but we did measure, as mentioned earlier, we measured the carbon to get it on a truck from the factory to the port, on a boat from the port to New Zealand. So the cost of that structure was about 10% dearer. Now, all of that 10% was in the floor system. So on a concrete floor, we have acoustic and fire given. In a timber floor, we have to use layers. So the additional cost on the structure wasn't in the structural elements. It was basically adding what we could call a computer floor or a floating floor on top of the CLT. So, I mean, you could bullshit and you could hide that in the fit out, for instance, but in reality, for it to perform the same as a concrete floor, we had to add this composite floor. The good thing about it, it creates a great cavity for services, and it is relatively cheap. And it can be a complicated computer cradle system, or like we've often done, I think we just did one at Redwood School, it can be a 3x2 on edge on a little rubber pad with stable flooring. So it doesn't have to be complicated, it can be relatively cheap. And that was giving us a acoustic separation and a area to run services as well. So we're getting all excited now. So we thought we will measure an apartment building that we just completed. I'm trying to think who designed this. Any engineers going to own up to it in the room? Can't recall. So this was built in concrete and steel. So we designed it another 2 ways. We did it in timber, totally in timber, engineered timber beams, columns, panels, floors, structural steel bracing, and then the second one was more of a hybrid. Okay, so we had steel beams and columns included. We then started measuring all our materials, just a summary of how it goes, and we can see the 3 different versions there. Again, still quite a lot of concrete and steel, predominantly from the foundation requirement. We then measured the carbon, and there's the difference. So even in the hybrid structure, you're still looking at sort of a 90% saving in the carbon in your structure. And I won't show any other examples, but basically between the, let's work here, between the 2 on the right-hand side, we have a nominal saving in carbon but a massive increase in cost. Okay, so if you want to take all your seismic loads in a relatively tall building through your timber structure, you can certainly do it. And we've got some examples of ones we're doing at the moment, and it's great fun and it's really good to build that way. But our experience is that that's a significant cost premium. So we're doing some buildings at the moment with sort of 300 thick CLT walls with McAloy bars and dampeners, and they're cool to build, but they're very expensive. In summary, with that exercise, a building like that office building is about a third of the total cost of the build. Okay, so ultimately it's going to be a 3% premium if you design it appropriately. That's what we believe. If you listen to some of the timber suppliers, the Red Stags and that, they'll say, look, we can build it for the same price or cheaper. I don't think you can. I actually think from our experience pricing these projects and building some of them, it's going to be a premium, but it's going to be quite small. If you can design it appropriately and you can save that amount of carbon for maybe a 2 to 3% premium, it's still very saleable. You know, I don't think it's ever going to be super cheap, but it doesn't have to be expensive. If you're designing a big span open office building, don't do it in timber. It isn't fit for every purpose. You know, the elements are bigger, it sags more. But if you can control that and you're happy about using hybrid structures, it's certainly got great opportunity. In terms of lessons that we've learnt on the way through, hybrid buildings deliver impressive carbon savings at a comparable cost. So that was a big one. So no matter how we measured it, and this gets right back to, at the moment, we're working on a design for a simple, the warehouse, you know, the red shed. So big portal frames, and we're doing one in timber. So we have LVL portals and we have LVL purlins, I think. And the engineer designed these great big timber columns in the middle to hold it up. And it was expensive, and from a retail point of view, quite ugly. So take your big timber column in the middle and change it to 125 RHS and paint it white, and it disappears. And it's really cheap and it's really light, and it changes your carbon values bugger all, but it makes the commercial reality of the building work. So if we'd stuck to it's all got to be 100% timber, the client wouldn't build it. It was just too expensive. So if we want to get more timber involved in the industry, we have to, I think, this is a personal view, we have to be more flexible with some of those details. Utilising concrete and steel, so that's another hybrid structure we did there. We've sort of pretty much covered that on the yarn on the way through. Cost comparison, so we actually measured one. So we're doing a timber job at the moment, and it's got, you know, the big shear walls and timber and dampeners and all sorts of things. And the cost of that shear wall is $1,400 a square metre. If we designed it in situ concrete, it would be half of that. And that's taking into account that we're going to have to make it a bit heavier because we haven't got that ductility. We're going to more elastic design. But if we design it in precast concrete, it would be similar as well. So that's the magnitude of difference in the seismic elements. It's sort of double on the exercise we've done. So certainly don't want you to discourage you from coming up with really cool seismic timber designs. But if cost is a factor for your client, you need to consider other more sort of regular designs. The other thing we come across is also designing for the material. So standard New Zealand LVL comes 1,200 millimeters wide and 12 meters long. It can be spliced to longer lengths, but it can be expensive and a little bit ugly. If you have trying to think about a simple example, so you have an LVL portal frame and you cut it into this really cool triangle, you're going to throw away the other piece of LVL, but you're also going to pay for it before you throw it away. Okay, so again, we come across this thing, we'll price the job for an architect and they say, oh, but the LVL supplier told us it was $2,000 a cubic meter and it's working out at $3,000. And we have to point out, well, you realize it comes like this and you've just cut a whole lot out, and that's gone to the chipper and has been now used for fuel by Nelson Pine or Carter Holt Harvey. So it's important that designing it, you recognize the limitations of the material. So LVL, 1,200 wide, 12 meters long. If you want it any longer, it gets expensive. It comes off the production line, goes somewhere else, gets detailed and spliced and comes back. If you have a funny shape, you know, if you have say a 900, let's say an 800 rafter, you've got a 400 column there you can use. If you cut funny shapes into it, just be prepared to pay for it. Glulam can be made to any shape, form and length, but generally more expensive. Okay, the other thing I'd quite like a bit of feedback from everyone or anyone in the room is standard size CLT. So you know how we have pieces of die-core and they're 1200 wide, and we have double T's. If we were to produce the global a CLT panel that was a standard floor panel that all you people out there would specify, what size would it be? Because if we can produce a product that goes from bespoke to commodity, the price will come down. So you know how you buy your jib board in 1200 wide sheets and they're 2.4 or 2.7? You tell me, and please email me, you know, what would your standard size CLT floor panel be?
I reckon that's 3.6.
3.6 wide? How long?
2.4. What?
2.4 at 3.6 in advance and 2.4. 10 meters?
You want to cover a typical interstory height.
This is floor panel.
Okay.
So floor panel. So I'll tell you where I'm, without trying to influence anyone, if we took a typical office 8 meter by 8 meter grid, okay, so typical Kiwi sort of grid size, and we accepted that CLT circa 165 mil is going to span about 4 meters, give or take. If you divided that grid into 3, so you had a 2.66 CLT panel and it was 8 meters long, we'd still need a secondary beam through the middle to you know, to take the load and deflection, but we're not adding any more UDL really. So the structure isn't getting much bigger, but we're adding one secondary beam. And if you did that in a brick pattern, would that be better transferring the load? So honestly, I'm seriously, if you can tell me what a commodity size product would be, that means that we can go and buy a standard product. We don't have to bespoke everything. And if we can do that, the price will come down by a third. And you can go to Bunnings and buy a CLT floor, give or take. So please, you know, serious, have a think and let me know what you think.
There's also what you can get on a truck as well.
Correct. So
you're going to pilot at 3.1.
Yep.
So you need to take that into consideration as well. And then you've got the length and the crane and the weight.
Yep. And if it's on edge, you can only get so many. If you can stack them, you get a lot more because it's light. So yeah, just by all means, Scott.Watson at Naylor Love. And we'll put a sticker on the bottom and say it's your idea. But you know, so really roughly, you know, you'll know more. But say I was talking to Alistair Cantner from Dunning Thornton, we do a bit of work with the other day, and he said, oh, you know, want a 200 thick panel, and others will say we need 145, and I'm sort of thinking 145 plus a bit of charring, maybe 165 in that sort of order. But you know, you're sort of spanning that 4 meters approximately. Let me know. Some examples. So at the Tauranga Airport that we built, and the architect chose to make the portals look like that, which is quite stunning, but we did them in glulam because they're a funny shape. Redwood School, you could say it's butt ugly, but it's a standard shape, and it's regular, and we did them in LVL, albeit we did splice them to get them to go the length. But they're two really simple examples in terms of horses for courses. That's perfect for its use. You'd be wasting your money doing that in glulam, but you'd be killing yourself to trying to do that in LVL. So just remember the materials that you're specifying, working in. Really, really roughly, a standard LVL structure, you'll get the base material for about $2,000 a cubic meter. For a glulam structure, it's going to be closer to 3,000. But it's very easy to get them mismatched and carried away in terms of sizes and quantities and wastage.
What's CLT?
CLT, if I'll be careful of this one. Probably, look, to be fair, 1,800 a cubic meter. That needs to be about 13 or 14 to be comparable to concrete and steel. Yeah. Pre-COVID, we could import spruce for about 30% less than we could buy it from Rotorua. I think that's probably changed a little bit now. It's probably getting a little bit balanced. And when production gets ramped up with CLT, it should come down. And when you guys tell me the size that you will specify, it'll come way down. You'll be building your houses out of it. The exception to the rule, there's always one, is Scion, stunning building in Rotorua. Has anyone been there, had a look? It's pretty cool, isn't it? LVL's cross-banded, so you'll see on the left here, LVL normally runs this way. It's running the other direction. So they can splice it into various joint components. And effectively, the exterior of that building is a diagrid. So that sort of eggshell effect, so it's complete diagrid, it works as a whole. There is, you probably can't see it very well, but in between those diagrids, there is, I suppose you could call them fuses. So there's the weak link, the little steel fuse. The building can move around and those fuses can be replaced. It's in Rotorua, sitting on top of a volcano, so it's got to be able to move around. We didn't build this one, but some of the lessons learned is when you're building is protecting your timber from moisture. So this one in particular had issues because all the end grain, probably hard to see, all this is end grain of LVL. Water runs down as a triangle, there's nowhere to go, sort of expands and gets bigger and gets a bit ugly. So you have to really think, if you're doing a building, how do you do it, how quickly can you put it up, and how do you waterproof it, either on the way through or very rapidly afterwards, and how do you manage the moisture during the construction. So if it's a CLT floor and it gets wet, it's often as simple as squeegeeing all the water off every day. It's not rocket science, but if you leave it there, it'll get moldy. So it doesn't have to be complicated, we just need to consider it. Treatment's another part of the material design. So LVL, really easy to treat to 1.2, so that's great internally. You can treat it to 3.2, but again, you're taking a material and you're adding quite a lot of expense to get it up to 3.2. My advice was, if you're in the 3.2 region, go to glue lam. If you have a rafter that's going from inside a building to outside a building, and it's an LVL, you're probably going to have to protect it. If it's in glue lam, you can leave it exposed. So again, it's just, and these aren't necessarily engineering decisions, they might be architectural, but it's just being aware of those factors and those when you're selecting those materials. The spruces and larches that all come from Europe, we like to call them naturally resistant as opposed to untreated, because the council hates that word, untreated. And look, the fact is the rest of the planet's been building out of those materials forever, so we shouldn't be scared of them. We just need to detail appropriately. Without sort of taking the piss totally off concrete and steel, the concrete industry is doing its bit. Currently, we can use concrete with up to 30% of fly ash replacing the cement. So you're effectively taking 30% of your CO2 equivalents out of your concrete. I think next year there's some material coming off the east coast of Australia, and we might get it up to sort of 55. So that's good. There's a note there about N-class reinforcing. It doesn't really apply to New Zealand because of our seismic code, but in other countries it doesn't have to be E-class. And we have now got one steel mill that's trialled producing structural steel from a hydrogen-based fuel. So you'll see there's lots of articles from concrete and steel saying, hey, steel's really good. And this isn't an anti-steel or concrete exercise, but the fact is that they all have to do their bit. This won't go down terribly well with your clients. Press pause. So pretty much, if you're silly enough to tender a job and not negotiate it with no love, well, then it's your own fault. But basically, with timber, you have to complete your detailed design in conjunction with your supplier of your materials. You have to complete your shop drawings to 100%, and you have to have your production slot booked. If you don't have your production slot booked, your project won't be built. And when I say it won't be built, it doesn't matter how many men you put on site, you won't have your timber, and it won't arrive till the next production slot's available. And it's going to get, you could say worse, it's going to get more intense as timber goes up. So it's really important, either to have a ECI period at the start where you bring your contractor or your supplier or both on board preferably, and you complete the detailed design. It's really critical that the shop drawing process doesn't get used to complete your design. So many times, someone was laughing over there, knows what I'm talking about, as the shop drawing goes in and it comes back and it's all changed. And this isn't just a check of the shop drawing, it's the design change. So that won't work in the timber world. It has to be complete, ideally in conjunction with your supplier, and then that production space booked. So it's going through a factory. They're not going to stop what they're doing just because you take an extra week to tweak your design on the drawings, or the contractor took too long to prepare them. Okay, if you can do that, if you can either push pause or start that process earlier, you're going to have a happy client at the end. There'll be less variations, there'll be less risk, be a whole lot less extensions of time and everything else. Does that sort of make sense?
Not.
And surely there's an opportunity there when you're using engineered timber, especially CLT, because you're getting program savings.
Yeah, and you can see, but those program savings won't work unless your material is there. So basically you're standing around with your hammer waiting for the truck to arrive. It's got to be, if I was doing a CLT building tomorrow in Christchurch, I wouldn't start till I had all the material in Christchurch, because at the moment it's got to come from Australia or Austria. So do all your planning. It's not a waste of time, but complete your design, complete detailed design, develop design, do all your planning, and then not only will it go smoother, but it'll go up quicker and it'll be less exposed to the weather. And that is a big factor. I mean, in Europe, a lot of these buildings are built in tents. You know, we don't really want to pay for that, but we need to consider it. With a bit of luck, I'll be able to open the carbon calculator and I'll show you. There's a couple of slides here. Any questions, which we can deal with in a minute? And we get asked this question all the time. Who would we recommend as timber engineers? And we say at the moment, there's only two. These blokes here. No, look, it is becoming more and more important through the whole, client base. Everyone's saying to us, how do we build it in timber? Who do we contact? So I think the Timber Design Society is a good sort of conduit to pass that information through. Everybody wants to learn about it. It is really easy to build an expensive building. And the worst thing we can do is to produce expensive designs, because it's going to hamper the progress of getting timber into it. So before I go into the calculator, is there anything else you would like to know or query or challenge? Come on, there's got to be something there.
I'm wondering, when you did the cost comparison,
Yep.
did you only consider material? Or did you consider also the savings on time in terms of preliminaries? The fact that eventually subcontractors will realize that it's easier to install piping and services into timber building rather than concrete building?
Yep, I'll go back to that one.
Because that's something which I think many QSs absolutely forget. If they get the timber cost, the material cost right, they still forget the fact that you might be able to lease the building sooner.
Yep.
And the contractor has less time on site.
I think that is very correct, and I think we will get there with a little bit of time and experience. Mm-hmm. For this exercise, we did ignore the shorter program, simply because there was acoustic questions we hadn't quite answered. There was supply chain questions we didn't quite answer. So there was enough questions there to allow us to leave a bit of a contingency. So I'm pretty sure within a couple of years you'll be saying, yes, you can build a timber building as cheap or the same price or cheaper. But I think at the moment, from the stuff that we've priced, none of us are smart enough yet to, for instance, we're doing a job now where the McAloy bars are coming from England. They're $750,000 for the steel bars coming from England. We wouldn't have expected that if we were doing an exercise like this. So yes, there's a bit of float in that 3% for that particular building, and I think you'll pick that up, but maybe not this year or next. I think that'll come with experience. Yeah. Yep.
There's a lot of these structures going up, three-story multi-unit housing buildings.
Yes.
Pretty much stick framing is the timber option there, but obviously you try and pull away from the.
No, stick framing is good, but maybe CLT floor.
Yeah.
Yeah. So CLT as an economic unit is quite good if you're using it on the wall and you're trying to leave some of it exposed. Like a lot of buildings are designed where it's all covered in fire line or acoustic jib or something. I think if you can, we'll go back and let me explain it. This one here. So these are student rooms. So similar sort of thing in terms of your. So there's no other structural elements required in this building because of all the bracing control from the CLT. So walls everywhere in both directions. So really stiff building. So in terms of, this is a student room in front of us. one side of that wall would be strapped and lined. So we'd have gypboard giving us an acoustic barrier, a fire rating, and a cavity to run services for both sides of the wall. The wall on the other side will be left exposed because students are going to kick the crap out of it, and you want to see the timber anyway because you're paying for it. Then the design will be flip-flop. So as you go down that unit, that floor, the rooms are flipped. So there's a common wall with one side lined with gypboard for acoustic fire services, and then the next one's exposed. Does that make sense?
My
Yeah.
question is more related to, does the extra bit of timber and stuff used in the set frame come into your calculator as well?
Well, you can measure it, yes. Yeah, you can. If you're doing it that way, the CLT would be comparatively priced. If you decided to line both sides of it, you may as well use stick framing. Yep.
What are the main things the wood processing industry needs to do to support what you're trying to do?
The government needs to take control of the forestry again, because we're actually going to, if this works, we're going to run out of timber. So, and that's true. So New Zealand, I remember the government used to own a whole lot of forests and they sold them all. Yep. And we're the only country that doesn't have a regulated forestry industry. So people, particularly from China, are currently in New Zealand buying all our timber, as you would know, and they're buying timber that hasn't been planted yet. The supplies from Russia are getting closed off next year because the Russians did the right thing and developed their own timber manufacturing processing. So more and more countries are coming to New Zealand to buy our timber, and it's really easy for the forestry guys to sell it rather than produce this product. So if the government could somehow incentivize us to make a secondary product out of it, would be great. They're not going to write a check out, but one of the ideas that came through was, you know, for instance, if you were allowed to depreciate this building over 20 years, you don't have to write a check, but you'd get more than your capital difference in depreciation. So that there is ways that that could be done if the government would listen. But certainly there needs to be some incentive for people to stop selling the logs as a log. I mean, they're going offshore now, roughly speaking, for $130 a cubic meter, and we're paying $2,000 a cubic meter to bring it back as a piece of CLT. It's a huge, huge difference. So the manufacturing process is what's that? More than 10 times, for 18 times. So the raw product's only about 7% of the actual cost. So there's massive scope. And if you can think of a way, Dave, that would, you know, we can incentivize the government, it would be awesome. Carter Holt Harvey closed down their LVL plant in Whangarei. The sawmill, yeah. And the LVL plant's decommissioned as well.